Ramanujan for G is now available on the Google Play Store. Try it out for free.
So we continue our discussion with respect to Lenz's law and Faraday's law, right? So this is an interesting mix here that you have to understand. Okay, the mix comes from you know um, the interaction between electromagnetic induction and alternating currents. Why did we end up with alternating currents? Well, we end up with alternating currents because of electromagnetic induction. Electromagnetic induction, as a rule, right? See, batteries tend to produce DC, direct current, that is constant current, right? Forms of um, you know um, power, like for instance what you get from the plug, right? uh, Electricity as we know it, right, from a utility, those forms of power tend to be AC, or alternating current. And what it is, the way the current is produced, that makes it alternating. Okay, now alternating current is typically produced through because of an electromechanical element, which is driven by magnetism. Okay, so that essentially comes from Faraday's law. Therefore, wherever you have Faraday's law, you tend to have alternating currents. Okay, it is always possible to also rectify a alternating current and produce direct current. Okay, but it is not so straightforward. Okay, typically you have these rectifiers, they do the conversion. Okay, then there are other kinds of rectifiers which are also used. Okay, so can magnetic fields produce currents? Okay, Faraday's experiments explained that this is actually possible, that changing fields in fact produce currents. And so that is where we kind of look at Faraday's experiment. In Faraday's experiment, he introduced this idea of a toroid or a torus. Okay, so it is similar to a modern toroidal transformer. Okay, so now what he did was, and you have to understand exactly what he did. Okay, he connected a galvanometer, and we discussed galvanometer and we discussed magnetostatics. What does a galvanometer do? When there is a current, it is a magnetostatic instrument which produces a shift. Okay, now when is what he introduced was this kind of a circuit. On one side he had a battery. He did not deal with alternating current, as I explained, using electromagnetic induction, or with these power plant kind of generators. Okay, he did not involve generators largely tend to produce alternating currents. Okay, he introduced a battery. Batteries tend to produce direct current. So when he turned the switch on, okay, so he had a battery circuit on one side, then a toroid, and on the other side he had the galvanometer. When he turned the switch on, he saw that there was a transient current. So at that point, just when he turns on the switch, the current goes like that. Okay, so it's zero when there is an open. Then as soon as he turns it on, there is a period over which it. And so at that point, there was a, on the other side, he was seeing a spike. And that spike would produce a transient wave. So when he analyzed that idea, and as a result, then he did other experiments. Okay, one of those experiments where he had a coil and then he used a magnet, and he that then he able to say that it is an induced current. Okay, So what exactly is happening? As soon as you switch it on, there is a time varying current which then induces, which then this current produces a magnetic field. dB equals IDL cross R by R cubed. Okay. Now that magnetic field eventually reaches steady state, so it comes back to no zero. Okay, but there is a transient time when that magnetic field is time varying. Okay, and during that transient time, the galvanometer flickers. So a changing magnetic field induces a current in this side. Notice that these two circuits are separate. This is one circuit, this is another circuit. Okay, this circuit produces a current in the toroid, produces a magnetic field in the toroid. This magnetic field is carried to this part of the toroid. Now, in this part of the toroid, the magnetic field initially is time varying. dB by dt, d phi by dt. Okay, so and that is Lenz's law. Okay, minus d phi by dt is Lenz's law. So Faraday's law is the induced EMF is proportional to the rate of change of flux. d phi by dt minus d phi by dt equals EMF. Okay, that is basically Faraday's law. So you must understand how Faraday's law works. There is an induced current through a time varying magnetic field. Okay, so that's what decides this. So now if you have a magnet, then there is a induced current, then you can, let's say you have, in this case you have a closed circuit, and the what is changing is the field inside this closed circuit, right? Therefore there is a dB by dt. What is the flux? Flux is B cross A, right? That flux is changing when you do that, and that therefore induces a current through this circuit. So if you put a bulb here or here, it will light up, because you are, when you do this, you are changing the magnetic field. Okay, so the magnetic flux is similar. So once he introduced this term magnetic flux, there is of course the electric flux which we have in Gauss's law, right? E dot dA, right? E dot dA is the electric flux. Okay, electric flux is a scalar. Similarly, B dot dA is a magnetic flux, and magnetic flux is also a scalar. And the rate, the time varying side of the magnetic flux produces an EMF. Okay, therefore, this is the basic idea behind induced currents. And then there was Lenz's law, who said that the nature of the current is such that it will oppose the magnetic field, it will oppose the changing magnetic field, much like Le Chatelier's principle. Okay? The system will react in such a way, if there is a change made to a system will react in such a way as to oppose that change. Just like Le Chatelier's principle, Lenz's law also says that the induced EMF will be such that it negates the others, the what caused it. Okay, so keep that in mind. So that's why you have the minus. EMF equals minus d phi by dt. So now what is the EMF? It is the E dot dl, right? dv by dx is E. So closed path integral E dot dl will give you the EMF. Okay, therefore you can then, that is equal to minus dv by minus d by dt of b dot da. Now when you learn Maxwell's equation, they will introduce Maxwell's equation in the following form: del cross E equals minus B dot. Well, for that you have to understand this idea of the curl, and then you can try and better understand how to make this work. Okay, so so let's continue now with our discussion of how how a magnetic flux works. In magnetic flux, phi b equals b dot dA is greater than 0. If b increases with time, then d phi by dt. Therefore, you have that time varying magnetic flux producing your EMF. Okay, so magnetic flux phi b equals integral b dot dA. B decreases with time, d phi by dt is less than 0. Induced EMF is greater than 0. All right. So moving magnet induces current. Okay, so if you had a loop, then you introduce a magnet inside that loop, then that magnet, moving magnet, produces a time varying magnetic field that will then induce a current. So a lot of these batteries and generators largely rely on this one principle. Okay, so the direction of the induced current. So if you go this way, it will produce a current this way. If you go this way, it will produce change the current. So what does that do? It changes the current one way to the other way, one way to the other. So you have that switch, right? Therefore, the induced EMF changes direction. That's how you end up with a sine wave in alternating current. There is a changing electromagnetic field leads to an electric field and the current being induced in a surrounding coil. Basis of the idea of generators and other electrical implements like generators. So let me take brief moment to discuss the relationship of this to AC. Most power that comes from AC. Then we use all these other elements. Okay, sometimes those elements are passive elements. Passive elements are elements like um, um, resistors, capacitors, inductors, which are naturally made. But then you can also synthesize these using transistors. Transistors are active elements. So you can synthesize these same elements using other elements. Okay. So circuits are made using a combination of a very interesting combination of elements, and that is the subject in itself. Small circuits are made, and that is taught in this field called analog electronics. Okay, mostly, largely two types of electronics. Okay, one is analog electronics, and the other is digital electronics. Electronics is little different from electrical circuits. Okay, electrical circuits involve larger currents. Okay, now electronics, on the other hand, involves low currents. Okay, so the currents are in milliamperes and microamperes, and the and understanding how these currents behave and act is a very much a part of how we look at electronics. The basis of the idea of generators and other electrical implements like generators. Okay, so now, as I said, right, the power generated by these dynamos, generators, etc., whether it is hydroelectric power, whether it is thermal power, right? Thermal power involves what? You burn a fossil fuel like coal, and then that drives some kind of an engine, which is then converted to past used. You then use electromagnets to, because it's rotating, it creates a time varying magnetic field. That time varying magnetic field then produces a, so you have a, let's say you have two magnets, okay, north and south pole. In the middle of it, you then rotate a, let us say you rotate a circuit. Okay, the power from thermal power, steam driven power rotates, causes a rotative motion, right? How does the car and the steam engine go? Class 11, if you attended yesterday's class, is explaining exactly this, right? Like that. Now in between a magnet, you then put a coil, and then you make that coil rotate. When you make that coil rotate, it produces a time varying magnetic field. The B dot dA of that coil keeps changing. When that B dot dA changes, you then have a induced EMF. And so that B dot dA is what? So let's say the B is like this, right? So the A keeps changing. When you rotate it, the B may not change. The B can be steady, but the A could be changing. If you change both B and A, still you will get some kind of an answer. More complicated. Okay. But if you keep a steady B, then you change the A, you will end up with B dot dA. Okay. So here there is a uniform magnetic field. B is increasing with time. Okay. So dB by dt is continuously increasing, 0.04. So now if you have dB by dt, the induced EMF is B times A. And you take phi equals B times A, and then you take the time derivative, right? But B is what? B is changing, right? B is dB by dt is set at 0.04. So 0.04 times pi r square will give you your EMF, right? The B is continuously increasing. B keeps on increasing. What happens? Eventually, there's too much B, right? But you never have that situation. Most often, that's why you end up with alternating current. You cannot have current going up in one direction, right? The EMF going up in one direction, right? So, the B going up in one direction. Most often, it is the A that is changed. Okay, that's why we always rely on alternating current from induced EMF. Now, a solenoid is a rod wound with a wire, many turns. Okay, so turns is a very important idea in a lot of these things. So it's a rod with turns. Solenoid is a n turns per unit length. So typically a electromagnetic rod, so like an iron rod. Okay, so the current through it is I, and therefore the magnetic field is B dot dl equals mu naught I, mu naught Ni, right? So now you can then look at the the corresponding, the magnetic flux per turn is B times A. So mu naught I times pi r square is the area. B dot dl equals mu naught I, right? Now you then have the A times the area, the flux is given by B times A, right? So mu naught Ni times pi r square, that will give you the total flux. So the total flux is mu naught Ni is the B times pi r square, right? And therefore the total flux through S2, so there is another coil inside, which then receives the current. So this first one produces the field. The other one receives the corresponding total flux. Okay, so the induced EMF calculations is given by that, but remember that you need a changing magnetic field, So inside the solenoid, you have to have some way of changing the magnetic field. Okay, and so the most common way, as I explained, is little bit uh, is caused by some kind of varying the B or varying the A rather than the B. Okay, so the EMF is E dot dl, and therefore it's minus d by dt of B dot dA, right? Therefore you end up with u naught Ni, and then you have a di by dt, right? And therefore you have mu naught Na by 2 pi r di by dt, right? Therefore you have an electrostatic field. Number of turns n equals 1000. Therefore if you have A, then di by dt, which is in amperes per second. The area of the solenoid is given. So this is the solenoid case. My suggestion is, with an induced electric field, my suggestion is you take a look at the associated IIT PAL lecture as well. These are very well taught by the professors, and you will learn a lot by understanding this. So now a changing B produces an induced electric field. Okay, changing B del cross E equals minus B dot. Changing B produces a electric field. Now, the induced electric field, changing flux during the motion is EQ plus Q times V cross B, right? And therefore, you also have the induced flux, changing flux due to the motion is what causes the Lorentz force. So in this case, let's say you have this I times L cross B, right? As you apply this force, magnetic force is I times L cross B, right? And the I is E by R, right? Let's say it has a resistance, right? The induced EMF is E. Remember, EMF is a voltage, right? V by a voltage by R is the induced current, right? Therefore, and the magnetic flux is what? I times L cross B, right? Therefore, you end up with so the induced current is V times E times L, or the E is equal to VB, right? As we EQ equals QVB, right? So you can cancel out the Q's, and therefore you have E equals VB, right? And therefore this E is EMF, so it is um, 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 EMF is what? E times L, right? And E is V times B, so V times B times L by R. The magnetic force is I times L cross B. Therefore, you have I times L, and the you therefore have L times B, and then for the I, you have V times B times L. Therefore, you have B square L square V by R. Okay, so changing flux due to motion. Okay, so now you have motion, there is changing flux. So how do you evaluate that? Q times V cross B, you set the force to be 0, EQ equals times. Okay, so so what is the work done? Work is the work done per unit time is the power. The power is the force times the velocity, right? Force times the velocity. So you have another V. So B square L square V square by R. And so if you had heating, you have correspondingly I square R. Okay? These are essentially to help you understand how induced EMFs behave. Okay? So my suggestion is that you try to understand how there is an interaction between B, time varying B, and the induced EMF. So with that, I will switch back a little bit to so now when we look at so there are induced currents in all sorts of things. So in a transformer, in order to prevent these induced currents inside the transformer, what they do is they slice up the cores, and so that they introduce what is called lamination. Lamination reduces these excessive currents, which then waste power. Okay, so because of that, they kind of slice it up and they introduce laminations into these transformers to prevent what are called eddy currents, which are a negative. Okay, so eddy currents are very important, and they have important applications in electric motors, as well as, most importantly, transformers. Heating in transformer is prevented by laminating the core, which is basically you slice it up so that there are fewer pathways for these currents. Now, uh, a transformer works through this process called mutual induction. So if you have one current that then induces a and the basic idea in this is this thing called an inductance. Okay? An inductor is something in which there is an induced current. So inductor is shown like this. uh, Resistor is shown like that, inductor is shown like this. capacitor is shown like this, or it is shown like this. Two parallel lines of same length. Two parallel lines of unequal length is a battery. Two parallel lines of equal length is a capacitor. Okay. Now, an inductor is a coil, because typically it is a self-inductors which are called inductor. Now, a transformer, on the other hand, involves what is a mutual inductance. Mutual inductance, you have one loop producing current in another loop. If a current produces in the same loop, it is called self-inductance. Okay, so now, the case of mutual inductance, you have phi equals mi, and therefore phi equals Li is self-inductance, phi equals Mi is mutual inductance. So the mutual inductances from one side of a transformer to the other side, M12 will equal M21, and usually it is mu1 n1 n2 pi r1 square L. Okay, how is this evaluated? The magnetic field is mu times Ni. You already know that. Now the magnetic field through the other one is the magnetic flux through the other one is mu times Ni times pi r1 square, right? And this flux through the length L of the solenoid 2 is magnetic flux pi Ni pi r square times N2L. Okay, and therefore this whole thing, if you remove the I, everything else is your M21. Okay, so the flux phi equals one large multiplication times the current. Okay, so M2I, right, will give you phi. Okay, so that produces your mutual inductance. So what do we how do we now relate this to the other set of subjects that we have been looking at?